to Pipro versus YouTube channel where curiosity meets the code. Today our topic of discussion being deep learning. So let's get started. So firstly, I'm going to introduce you to deep learning. Then we have power of deep learning, major algorithms of deep learning, convolution neural networks, that is CNNs. We're going to discuss about RNNs, which is recurrent neural networks, then long short-term memory, which is LSTM. Then we'll be discussing about transformer, generative adversarial networks, that is GANs. Then we have autoencoders, we have deep Q networks, capsule networks, then applications of deep learning. Then we have some of the challenges and future of deep learning. So let's get started. So firstly, what is deep learning? So deep learning is a subfield of artificial intelligence, which we have discussed in the previous video. It is inspired by structure and function of the brain. And we have what is the power of neural networks, uses artificial neural networks for complex pattern recognition and learning, mimicking the brain's ability to process information. And then we have the world challenge impact, that is revolutionized fields like natural language processing, computer vision, robotics, healthcare, and more. So as in the previous video, I told you artificial intelligence mimicking the intelligence of our human thinking. So it starts from how your neurons work. So how your neurons work, that is neural networking. The entire thing is called deep learning. The way we process things, the artificial intelligence or deep learning should also be able to do. That's the future of deep learning. Next, we have the power of deep learning. So what is the power of deep learning? So I'll take a few everyday examples. Deep learning, powerful features like facial recognition in your phone, voice assistants like Siri or Alexa, and personalized recommendation on streaming platforms. So basically, when you see a person, you are able to recognize that this person is this. So that's how your phone is also recognizing your face and unlocking your phone. That includes your voice assistants for Siri or Alexa, etc. Then beyond consumer tech, we have self-driving cars, which is basically the invention of the decade. Uses also deep learning for obstacle detection, that is which car is going in the front or which car is approaching us, etc. And safe navigation, while medical image analysis relies it faster and more accurate diagnosis. It also includes medical diagnosis, like when a system sees a couple of pictures, it will be able to recognize what kind of a diagnosis or he or she is having. So that is the power of deep learning. Next, we have some of the major algorithms in deep learning. The major one, which is convolution neural network, which is CNN. Then we have recurrent neural network, which is RNN. Then we have short-term memory, which is LSTM, transformers. Then we have generative adversarial networks, which is GANs. Then we have autoencoders. Then we have deep Q networks, and last we have capsule networks. So let's get into deep what is each algorithms perform. So convolution neural network, again CNN, are specialized neural networks adept at recognizing and classifying images, and their use in feature extraction. They employ layers of filters that act like detectives searching for specific patterns and features within an image, like edges, textures, and shapes. Then we have building the big picture. These extract features are then combined and analyzed by deeper layers, ultimately allowing the network to recognize the objects, scenes, and even emotions within an image. Next, we have some of the real world application. It includes facial recognition, as I discussed earlier. CNN power of face unlock feature in your phone, identifying you with remarkable accuracy. And then we have self-driving cars, which is they guide autonomous vehicles by recognizing traffical lanes, signals, obstacles in real time. Then again, medical image analysis. CNN helps doctors diagnose disease faster and more accurately by analyzing medical scans like X-rays and MRIs. Next, we have RNN. Again, unlike CNN that focuses on image, RNNs are excel at handling sequential data where other information matters, like the memory matters. They use internal memory to capture temporal dependencies, remembering past inputs and using them to interpret the current one. How do you understand this context? This memory allows them to understand the context in language followed, melodies in music, detect patterns in time series data. What are some of the real world applications? Firstly, we have sentiment analysis. RNN can analyze text to determine whether it expresses positive, negative, or neural sentiment, crucial for understanding customer reviews and social media feedback. Then we have machine translation, which is the power language translation tools enabling seamless communication across different languages. And then we have music generation. RNN can learn musical styles and create new original composition that mimic human creativity. The next algorithm is long short-term memory, which is LSTM. LSTMs are special kind of RNN designed to address the challenge of long-term dependency and vanishing gradient that can occur in traditional RNNs. Then they have gated memory cells, that is, they introduce a unique gating mechanism that controls the flow of information through the network, allowing them to selectively remember and forget important details over longer sequences. What are the gates in action? The gates in LSTM are to forget gate, that is to determine which information to discard from the previous cell state, and input gate, which decides which information to store in the current cell state, and then we have output gate. This controls which information to output from the current cell state. Then what are some of the long-term dependencies? It excels at tasks where understanding long-range context is crucial, such as understanding entire sentence or tracking patterns in time series data. What are some of the real world application? Firstly, we have machine translation. It is used for generating accurate and fluent translation of text between languages. Secondly, we have text summarization, considering long documents to concise summarize while retaining key information. Then we again have sentiment analysis, determining the emotional tone of text, which is positive, negative, or neutral. Then we have question and answering, which is automatically answering question based on text comprehension. Then we have converting audio recordings to speech into text, then even in noisy environments or with varying accents. Then we have voice assistance, which is understanding spoken commands and responding accordingly. Then we have stock market forecasting, which is predicting future trends in stock prices based on historical data. Then we have weather forecasting, which is anticipating further weather pattern based on extensive meteorological data. Then we have anomaly detection, which is identifying unusual patterns in data that might indicate fault or security breaches. Next, we have transformers. Here, attention is all you need. That is, transformers introduced a novel architecture that relies solely on attention mechanism dispensing with recurrent connection and enabling more efficient parallel processing and long range context awareness. Here the encoder decoder structure, they typically consist of two primary components, that is encoder and decoder. What is encoder? Encoder processes input sequence, that is text, code or audio, and produces an encoded representation that captures global relationships between elements. Then we have decoder, which generates output sequences, that is example translated text, summaries, code completion based on encoded information. Then we have self-attention mechanism, which is the core of transformer is to self-attention layer, which allows each part of the input sequence to interact with every other part, enabling the model to learn long-range dependency and contextual relationship. What are some of the real world application? It includes machine translation, that is achieved unprecedented quantity in translating text between languages, surpassing traditional RNN based models. Then we have text summarization. This produces concise and informative summaries of long documents, extracting key points and preserving coherence. Then we have question answering, which is effectively answer questions based on larger text corpora, understanding complex queries and reasoning over context. Then we have text generation, which is create realistic and creative text formats such as poems, codes, scripts, emails, and more. Then, of course, we have chatbots, the power for more engaging human-like conversation, maintaining context, and adapting responses to the user interactions. Next, we have GANs. This is a two-player game. That is, GAN consists of two neural networks competing against each other. That is the generator and discriminator. The generator is responsible for creating new realistic data samples, that is images, text or sounds, whereas the discriminator is tasked with distinguish between real data and generator's creation. Here, the creative adversity, this adversarially training drives both the networks to improve. The generator learns to create more convincing fakes to fool the discriminator. The discriminator becomes more adept at spotting fakes, forcing the generator to elevate its game. In supervised learning, GANs don't require labeled data, enabling them to learn complex pattern and generate new data from scratch. What are some of the real world applications using GAN? We have photorealistic image generation, which is creating images that are nearly indistinguishable from real photographs, including faces, landscapes, and objects. Then we have image editing and manipulation, which is seamless editing images, altering elements, or transferring styles between images. Then we have resolution, which is enhancing the resolution of low quality images, restoring detail and clarity. Then we have image to image translation, which is transforming images from one style to another, example, day to night, sketch to photo. Then we have text generation, which is creating realistic and diverse text samples, including poems, code scripts, and emails. Then we have music generation, which is composing music that captures different styles and genres. Next, autoencoders. We have self-supervised learning. Autoencoders learn to represent data without explicit labels, making them valuable for unsupervised tasks and exploratory analysis. We have comparison and reconstruction, that is, they aim to compress input data into lower dimensional representation, which is encoding, and then reconstruct the original data from the compressed representation, which is decoding. What the architecture, it consists of two, which is encoder, which takes the input data and produces a compressed representation, often called the latent code or bottleneck. Then we have decoder, which takes the latent code and attempts to reconstruct the original input data as closely as possible. Then we have dimensionality reduction, which is the compressed representation can capture essential features and patterns in the data, enabling dimensionality reduction and data visualization. Then we have anomaly detection, which is autoencoders are sensitive to anomalies as they often struggle to reconstruct data that deviates significantly from training distribution, making them useful for anomaly detection. Next, what are some of the real world applications? Firstly, we have image compression, which is reducing image file size while retaining quality, enabling efficient storage and transmission. Then we have denoise images, which is removing noise and artifacts from images, improving clarity and visual appeal. Then we have feature extraction, which is extracting meaningful features from images or text from for downstream tasks like classification or clustering. Then we have recommended systems, which is learning user preferences from past behavior to recommend relevant items. Then we have anomaly detection, which is identifying unusual patterns in data that might indicate faults in industry systems. Then we have fraudulent transaction or medical conditions. Then we have drug discovery, which is identifying potential drug candidates with desired properties of learning latent relationship of molecules. Next, we have DQN, which is Deep Q Networks, which is hybrid powerhouse. DQNs combines the power of reinforcement learning, which is RL, and deep learning to learn optimal behavior through trial and error stimulated environments. Q learning on steroids. Leverage the Q learning on an RL algorithm that assigns Q values to action, representing the expected reward from taking that action in a given state. That is, DQNs use deep neural network to estimate these Q values, enabling them to handle complex state action spaces. Then we have learning from experience, that is, DQNs operate through an experience replay mechanism, storing past experiences, which is state, action, reward, next state in a buffer. Then we have network is then trained by sampling from this buffer, allowing it to learn from a diverse set of experiences and overcome problems like correlation between consecutive actions. Then we have target network trick to combat overestimate the of Q values and improve stability. DQNs utilize a separate target network updated less frequently to provide more stable estimates for learning the main Q networks. What are some real world applications? Firstly, we have mastering games. DQNs have achieved superhuman performance in complex games like StarCraft and Go, demonstrating their ability to learn optimal strategies through trial and error. Then we have robot control, which is Duke powered robots can learn to navigate their environment, manipulating objects and complete tasks like walking and grasping. Then we have resource management and logistic and scheduling problems. DQNs can optimize resource allocating and decision making for improved efficiency. Then we have medical diagnosis and treatment by analyzing medical data. DQNs can potentially assist in disease diagnosis and personalized treatment plans. Then we have financial trading, which is DQNs can learn optimal trading strategies in financial markets, although real world implementations require careful considerations. Next, we have capsule networks. It is a hybrid powerhouse that is deep Q networks, which is DQNs combine the power of reinforcement learning and deep learning to learn optimal behavior through trial and error in simulated environments. Then we have Q learning on steroids. They leverage Q learning and RL algorithms that assign Q values to action, representing the unexpected expected reward from taking that action in a given state. DQNs use deep neural networks to estimate Q values, enabling them to handle complex state action spaces. Learning from the experience, DQNs through an experience replay mechanism storing the past experiences in a buffer. Then we have the network is then trained to sample from this buffering, allowing it to learn from the diverse set of experiences and overcome the problems like correlation between the consecutive actions. Then we have targeted network trick to combat conversation overestimation of Q values to improve the stability. DQNs utilize a separate target network updated less frequently to provide more stable estimates for learning the main Q network. Next, some of the real world application will be similar to the DQN. So firstly we have mastering the games, robot control, then we have resource management, medical diagnosis and treatment, and then we have financial training. So some of the total overall application of deep learning, it includes computer vision, which is deep learning powers applications like image recognition, which is unlocking your phone with your face, and then medical diagnosis, that is analyzing x-rays and scan, and object detection, which is autonomous vehicles, navigation roads. Then we have natural language processing, which is machine translation, bridges language barriers and sentiment analysis, gorgeous online opinions and chatbots provided virtual assistants, all fueled by deep learning. Then we have speech recognition, which is voice assistants like Siri and Alexa rely on deep learning to understand your spoken commands, while automated transcription software converts audio to text efficiently. Then we have robotics, from navigation of complex environment to manipulation object with precision. Deep learning empowers robots to interact with the physical world in increasingly sophisticated ways. Then we have finance, which is fraud detection system, identifying suspicious activity, risk assessment, model prediction, further trends, and even autonomous trading strategies utilize the power of deep learning. Next, we have ethical challenges and future of deep learning. The first is ethical consideration. Bias in training data can lead to biased algorithm, raised concern about fairness and discrimination in application like facial recognition. Then we have interpretability. Understanding how deep learning models make decisions is crucial for building trust and ensuring responsible development. Then we have computational complexity, which is training deep learning models require significant computational resources, posing challenges for accessibility and scalability. So that's it for today. If you want any other topic to be discussed in PPT format or explanation required, comment down below. Thank you so much for watching. If you have learned something from this video, please do like, share and subscribe to our channel. Thank you.